So I think that this we are starting now to look at. So for example, wet coal is a very, very important. In South Africa, we have a lot of coal. Okay, coal-fired power stations. I know we won't. Let's say 20 years time, we won't. But now we do. And so now our electricity supply utility, Eskom, is very keen to know the moisture content of the coal. And so there can be a case there for the 3D because then you really want to look through the coal and see. So we'd be able to image each piece of coal. Then there's been fraud where people put something like it could put some oil on the coal to increase its calorific value when actually it's mostly, let me say, sand. And so those kind of things could also be diagnosed because of the 3D. So I think we plan to start. So in fact, we start very, very soon to look at this in the coal context as PolyPET in the coal context and see if it was looking for landmines or we were also hearing about homeland security, the borders and so on. I think, you know, we got the range of the 500 keV coming out. So we could activate the ground, for example, with landmines. So we also have this as a proposal, but I would say we haven't done much work on it, but it's a proposal that you activate the ground. You could activate to, let's say, 30, 40 centimeters, maybe a bit more. And so if there was a landmine buried that deep, then you would have a PET isotope down there. And then you would use SPECT, the gamma camera, the 2D version, because you can't put a detector underneath the landmine. So you would image with a SPECT camera. And so those are all different things. So I think, I mean, we need more person power, and then we would start shunting those scenarios and just seeing how competitive PolyPET could be there.
Thank you. Tom, is there a question?
Yeah, thanks. So hi, Simon. I think it's such an ambitious use of nuclear technology in an applied space. I'm wondering, what's the drive for imaging the diamonds directly? You've got all these problems with attenuation, correction, and self-absorption. Just in terms of detecting them, it seems that it would be a lot easier to use, as you say, less Ds. But what's the drive to image them?
There are things that can also masquerade. There can be wood, there can be rubber in the rock stream. The diamonds are very, very rare. To get to see down to the smaller diamonds, you really need to see them in the carbon background of their own voxels. And you don't want to integrate the carbon background from wider ones. So it turns out the 3D is absolutely necessary in the diamond industry. And then there are a lot of ideas. For example, the people who do X-ray transmission, which is the closest competitor, they want one rock isolated presented to the scanner, okay? So they speed up the belt, and then the rocks, like traffic, you know, separate. And then they have one rock at a time going on under the scanner. It's just like your baggage scanner at the airport, dual energy X-rays type of technology. And they can segment to diamond. But in our case, we do better when there's a bed. So I don't know if you've experienced of PET, you'll realize that the edge effects are your enemy. And so if you can settle the rock into a bed, then you start to do better. So So we have to do a systematic correction for voids, basically, because the less scattering in a void, as you've just mentioned, the scatter problem, can actually look like more signal. And so there are those kind of systematics. And I think then the fact that PET likes a bed of rock, the opposite of XRT, is giving it a rate advantage. And so it just seems very, very nice. But you can imagine, you know, there's 1 carat per 100 tons. And I mean, you have to do a lot of rock. So you are lowering the energy and the water consumption, the carbon dioxide production, amount of plant, and then also the risk of breakage.
Simon, unfortunately, sorry, I was interrupting, okay. But we are too late today. We have been, so Nikita, thank you so much for your talk. I'm sorry, Nikita, I don't want to take over.
Okay, so thank you, Simon, and everybody. The next speaker is actually Tom, and we are already late for his talk. So I would like to give everybody a 5-minute break, just a quick bathroom or coffee break, and we'll get back in 5 minutes.
Thank you so much, Nikita.
Thank you, Nico. Okay, I think that was our 5-minute break for this morning. So our next speaker is Tom Leadbeater from the University of Cape Town. And you're already set up, so thank you for your contribution.
Thanks, Chair. Good afternoon, actually, to South Africans, but I think good morning to many people and good very early morning to quite a few people in various parts of the world. So it's so nice to be presenting to such a wide audience. So I'm from the University of Cape Town, the Department of Physics, where we do applied nuclear research. My expertise is really on nuclear instrumentation and nuclear physics, applied nuclear physics radiation detection. I'm part of a university research unit called Measure, where we're using nuclear and electrical measurement techniques to solve or address problems in applied sciences. So I'll give you a flavor of that this morning. Mostly talking about our PEPT enterprise, which is at iThemba Labs in the Western Cape. On the slide here, myself and collaborators and a number of students and other people that are involved in these various projects. So before we get into some of the details, I know we've talked about PET and medical positron imaging a little bit this morning already, but just to put it from a UCT perspective, this is our coincidence experiment setup that I think probably almost everybody in the audience is familiar with already. We have some sort of detector telescope with two radiation gamma sensitive detectors. These are large sodium iodide detectors. And they are set up on a detector telescope where you can change the angle between the two detectors and measure then the singles rates and coincidence rates for a positron emitting source placed between them. And this is in our undergraduate physics lab at UCT. And the students learn how to calibrate the two detectors, set up all of the electronics. Of course, they're used to doing this for a single detector, but you double the number of detectors. So 2 HV supplies, 2 amplifiers, single channel analyzer, coincidence time pickoff, and so on. And what they typically do in our lab, and even in COVID times, we managed to run this laboratory in a remote fashion. We would measure the angular distribution of the annihilation photons produced by positron emitting sources. We also do some other fun things in terms of timing and coincidence scaling. But to really make this a useful process, we in the laboratory we measure this angular distribution in the horizontal plane, but to make this useful on a large scale basis, you really need to go to many detectors. So here in my lab, we have a setup there where we have on both sides of the screen are segmented position-sensitive detectors with single channel analyzers set up to window on the 511 keV annihilation photons. I always have to refer to my notes because whenever I talk about this live, I always get the numbers wrong, but there are 512 individual BGO scintillator crystals on either side of the screen. And we're viewing then the live display. Each one of these little dots corresponds to one of the detector crystals. And when they detect an event, they light up with this white square. And what we're seeing at the moment then is a live display. And this is just the cosmic background and probably a little bit of activity, residual activity in the lab. So not very exciting, but becomes a little bit more interesting when you introduce a gamma ray source. And you can see here the position sensitivity of these detectors. This is a cesium-137 source. Again, probably everybody in the audience familiar with cesium-137. Being just a single photon emitter at 662 keV, we have some sensitivity to that. And you can see the detectors responding really through the inverse square law. You can see on the other side of this of the detector array, not much happening. So what happens when we introduce a positron emitter, again back to background, but here comes a sodium-22 source, and we're doing now a time correlation where we measure the arrival of the pairs of annihilation photons with a time resolution of around about 2 to 4 nanoseconds. And there, when we have those events, we're drawing then the green line between them. And the thing to point out, of course, is that one of the things the students were always very surprised about is, yeah, they really are back-to-back. The physics is real there, and we measure those back-to-back pairs. We can reconstruct those trajectories of the pairs of lines. And for a single point, we can measure then the position of that point in 3 dimensions and at a reasonably high spatial resolution. This is the basis of medical PET that we've heard about already this morning. But for a single point, all of these lines should converge on the position of the point. From our point of view, this also gives us an ability to measure a dynamic system. You'll see that I'm moving the sodium-22 source around, and this is just a calibration source from the teaching lab. It's not a very active source, but we can use maybe tens to hundreds of these lines to locate the position of that source to within a few millimeters in 3 dimensions. So this gives us a very powerful mechanism for measuring dynamic behavior using nuclear instrumentation techniques. So this is then just a summary of the sort of things that we're looking at. Again, these are BGO segmented scintillator arrays. This is something that we put together for really outreach work in the and demonstration of this. But we can use this system and types of this system for real research. And the detectors look like this. They're 8 by 8, so 64 crystals backed by photomultiplier tubes. We have analog readout, and we're able to determine the individual crystal element hit by the detectors. About 60 to 65% intrinsic efficiency with an energy resolution of 10% 511 kV, 4 nanoseconds resolving time. And we're digitizing all of these signals. So we're looking at large-scale arrays of detectors running up to megahertz data acquisition rates. So each one of these detector blocks here will provide data about a megahertz, a bit over. So we're digitizing data around about 10 to 20 megahertz onto disk. So we're using this to develop instrumentation techniques for positron imaging. And for other uses. This is a picture of my lab. Again, my setup in the background there. Nothing special, Nico. No special names here. Just I think probably Tom's garage or hobby room would probably be the right word for this. This is my playroom. Lots of detector instrumentation, electronics, data acquisition, development. Again, all keyed to the ability to measure then these annihilation photons. And just while we're talking about our developments of data acquisition systems, one of the things that we really do for these types of measurements, because we're interested in measuring dynamic systems rather than a steady state type image, which you would do in traditional medical PET, we're interested in measuring systems that are moving at high speeds. So we have a research program which is developing and optimizing the front-end electronics digitization data acquisition system. And JJ's talk the other day was very, very interesting for me in terms of the data rates. But we're pushing the total event rates, dealing with random coincidences, delayed coincidences, and so on. Really developing those systems to a high level. And this is a picture of me last year as my setup in the lab, and we're broadcasting coincidence event data over the Wi-Fi network in the lab to a Raspberry Pi, actually over here on the other side, which is able then to capture the data. So we're doing some clever things with network data acquisition for these positron systems. We're also, I haven't figured out a use for this, but a mobile phone app to do the same sort of thing. I really can't figure out why I would want to do that, but these are the sort of toy projects that undergraduate and maybe some of the less senior postgraduate students are potentially working on. So what's it all for? Here at PEPT Cape Town, this is at iThemba Labs. We operate this device, which is it's a unique ex-clinical medical scanner. For those of you that are aware of medical scanners, this is not a HR. It's not a HR plus, but it's a HR plus plus, which was a one-off system made for doing 3-dimensional imaging of patients, particularly brain imaging, to do it all in one slice. And the idea with this is they actually got two normal medical PET scanners and sort of joined them together to make this very, very large three-dimensional only system that was used for clinical imaging. It turns out there are all sorts of problems with doing that on a medical scenario. Eventually this system was decommissioned and moved to the lab that I now run at PEPT Cape Town, where we use this system still for positron imaging, but for industrial systems. And the sort of thing that this looks like here, we have a live feed from the detector, again for a point source. We use a fast algorithm to select those lines that are prompt coincidences and reject any scatters and any random coincidences. We reject those lines. We're not really interested in the lines themselves, but we're interested in measuring the position of a single point. The single point will be a tracer particle that is inserted into a system of interest, i.e. a physical system or an engineering system. And we're able, over a long time scale, to measure particle dynamics and fluid flow, in particular dynamic behavior. And the image here is an integrated image showing with the colors proportional to the velocity of the particles moving in the system. So unlike normal PET imaging, where you get a steady state distribution of the radioactivity, we're looking at and that's a Eulerian type approach of measurement. We're looking at a Lagrangian approach where we're measuring the trajectories of individual particles in the system. So it comes to the point now, and particularly for the students in the audience, just to make this comparison, what PET imaging is not. PET imaging tells us about function. It tells us about how material radioactive molecules are distributed within, in this case, a traditional medical PET image. This is a three-dimensional PET image. We see radioactive uptake in organs and in tumors, and we can measure biological function. A lot of students look at this image and say to me, Tom, the resolution is awful here. Why aren't we looking at this picture on the right here, where I can see very high definition, high resolution structure? And the structure is given by X-ray tomography. This is very high resolution X-ray showing the bone structure. And this is sensitive to density and Z, sensitive to proton number. So, and it tells us about the physical structure of the materials. It doesn't tell us how stuff is working. It doesn't tell us about function. So on the picture on the right, we have a combined image of X-ray CT, which is showing the bone structure, i.e. the physical shape and where the objects are. But these bright colors, the reds and the greens, are PET data that are showing the physical function, i.e. what the molecules are doing, how those organs are operating. So they tell us different and complementary information. The spatial resolution is slightly worse for PET, but it isn't really trying to show us the structure. So given that PET tells us about function of materials, and I think I've already got the idea across that we're looking at the motion of particles, we're looking at dynamic systems. When we're using these particular systems, we're looking at three-dimensional tracer imaging. It's non-intrusive. The gamma ray photons can pass through significant amounts of materials. So this means that we can directly examine opaque and dense systems, things that are interest to engineering applications and physics applications. We apply these techniques to both granular materials, so particles, grains of sand, glass beads, coffee beans, you name it. We've done all sorts of things in particles, but we're also able to study liquid traces with neutrally buoyant particles, again, following the flow behavior as a Bernoulli type flow. This slide's slightly out of date, looking at high speed for around about 1,000 locations per second, a little bit more than that really. We would aim to be able to locate a single particle to within its diameter 1,000 times a second. So we would be looking at particles moving at up to speeds of 10 meters per second. This is particularly relevant for engineering type applications, which I will say something about. And from a fundamental point of view, we measure position as a function of time. So we can measure then the time differential, we can calculate velocities, and we can calculate, to some extent, we can calculate accelerations of these systems. So this gives us a very powerful mechanism for studying dynamic behavior in 3 dimensions. The typical places where we're using these types of measurements are for system optimization and design. There are a lot of engineering, and in particular, as Simon's already shown us, some minerals type applications that use lots of energy or lots of raw materials, and we can use a knowledge-based approach to actively design to reduce wastes, for example. We're also interested in developing and verifying computational models and fundamental theories. So just to give some examples, and these are really toy projects, but I think the thing for me is that these are done by our undergraduate students at UCT. So this is 2019. This is a typical minerals type application. You have grains in a rotating drum here, and this is on a lab scale. We have multiple particles of different densities or different sizes, and the drum rotates at a certain rate. And there's a huge amount of theory and computation that can go into this. And this is of particular interest to the minerals and mining processes, because when we were looking at diamonds, for example, one of the things you would like to do is you would like to crush the raw ore, and that costs a lot of energy. There are a lot of computational models that talk about how these materials behave, but they need backing up with experimental data. So here, the middle picture here is a simulation. This is about 100,000 particles. It's about 4 seconds of data, and it took a few weeks to calculate by doing the hard body collision forces on each of the particles on a supercomputer. So a few weeks. And here is, on below, is the raw data acquired from our PEPT measurement, which is real-time measurement of particle dynamics. And we use these types of measurements to inform the physical models that go into taking to describing these systems, and in order to understand better the fundamental physics underlying the flow. So this is really, for me, one of the key outputs of this third year project, looking at 2 different species, the red species and the blue species, how they segregate, how they mix, and how they behave. And one of the things that is really of interest here, we do this on a lab scale, but when you look at these systems in a real scenario on a plant, this drum is sort of like this size. It's handheld, it's a lab scale size, but we're looking at finding out what the scaling laws are and how those systems behave when you extrapolate this to a real system on a mine, which may be of the order of 3 stories high of a building. So we're looking at measuring dimensionless parameters which describe the fluid flow, or in this case, the granular flow. Despite COVID, we managed to do a third year project this year in the lab, and this was done via Zoom with the lab technician Mike Van Heerden, who ran the experiment directed by the third years over the internet. And this was quite a challenge, obviously, but we did manage to get our third years into the lab. And the reason I put this slide in last night, it's fascinating. They needed something that they could do in a COVID scenario, but we were using PEPT to measure 2- and 3-dimensional Brownian motion in a system. So this is far more on a fundamental physics scale. And after watching Dean Lee's talk last night, where he was talking about diffusion processes and the Green's function Monte Carlo that is used to describe how, and this is physics that is far above my pay grade, but it's the same type of Monte Carlo modeling that comes into describing the motion of these particles. So the top data here, this is the same piece of Monte Carlo. It's a diffusion-based model to describe particle motion in a 2-dimensional system with some data and some fits. And here is then the measurements that we were able to do in the lab this year as part of the third-year physics program. So what I'm really trying to say here with PEPT is that it's an applied dynamic measurement technique which can be used for all sorts of interesting applications outside of nuclear physics. From our point of view, we're very interested in making tracer particles. For us, the tracer particle, obviously, it's non-invasive, but it needs to be representative of the material. And we would typically make tracer particles in the size range 50 microns to tens of millimeter diameters, and they would suffer all sorts of aggressive environments. Engineering situations are aggressive, high temperatures, high pressures, lots of engineering type mess. Ideally, we would like to dead time limit the detectors, and that means a huge amount of activity labeled onto one of our single particles. And traditionally, there are 2 places in the world where PEPT is done on a regular basis. There are a few other places in the world where people play with PEPT ideas, but at Birmingham University in the UK, they traditionally use fluorine-18, but we've developed, using the germanium gallium generator system, we've developed all of our radiochemistry is based on this. And we would say that we are probably the world leaders in applying germanium-68 radiochemistry to these particular problems in producing particles. We're very good at at grains and granules. We're quite good at mixes of multiphase flows. Those are turbulent flows with loadings of particles and liquids, which are very, very challenging to model from a physical theoretical point of view. And we're quite good at doing liquids as well. So we've developed over the last 10 years really leading radiochemistry to back up this enterprise. And in the last couple of years, I've been working with iThemba Labs on novel or new nuclear reactions, and then just to cite Eric Norman here, taking oxygen-16. So Eric's talk on, I think it was Wednesday, on the stellar evolution, taking oxygen-16, adding an alpha particle to make neon-20, and then knocking out NP to make fluorine-18. So the advantage of oxygen-16 is, of course, that's the high abundance isotope in natural oxygen. So we can now use alpha particle beam to produce fluorine-18 within the system of interest. So we're making particles that are chemically identical to the particles of interest with a positron-emitting isotope. So I think nature may have been doing this for a rather long time, although fluorine-18 decays to oxygen-18 and the oxygen-18 abundance is very, very low. So maybe Eric could have something to say about that. I've put some cross sections up, but we've done this experiment now at iThemba Labs a few times and shown that this is a viable method without producing too much waste. Just to talk back to Simon, we also see sodium-24 production from this, and it's from fast neutron interactions on some of the impurities in the systems. Sodium-24 is neutron rich, so it doesn't produce positrons, but it has a high energy gamma ray which pair produces, and obviously produces noise then in one of these systems. But we're understanding that to a good level now. So recently, we've had a bit of a period of consolidation. We now have a bespoke radiochemistry lab. This is a photo of our facility at iThemba Labs. There's our 2 pairs of our positron cameras, but we have a bespoke radiochemistry lab built into the laboratory where we're able to handle short-lived radioactive isotopes, positron-emitting isotopes, and we use this for tracer production materials characterization and development of the techniques. We've also had a bit of a calibration service and repair campaign, because when you have 32,000 detectors, the calibration drift over time is significant, and it's a bit like painting the bridge. Once you've calibrated all of them, the first one's ready to be calibrated again. And just to point out as well, we've had some recent appointments in physics in the last 4 years myself. Katie Cole, who is an expert on applying these techniques to particular systems in engineering and minerals applications, and Mike Van Heerden, who is the person responsible for the gallium radiochemistry. And we've undergone a bit of a rebranding, very subtle change of color of the logo, and being absorbed into the Measure Research Unit, where we're using these techniques to solve real problems in applied sciences. That's not all we've been up to. We're also growing. And I've been lucky enough to be awarded a very large grant to buy a new combined PET X-ray CT system, and I'm hoping this might actually arrive, COVID aside, this may actually arrive before Christmas. So we will be able to do those combined mixed mode imaging of PET and X-ray CT at the same time. We're developing on very small scale. This is cadmium zinc telluride segmented pixelated detectors on a very, very small scale. But we've demonstrated, and there's a publication coming up soon, demonstrated microscale tracking using these detectors for the first time. So that's a massive advantage. We've also, COVID really has forced this, but a lot of grant application writing this year to the NRF to support the students that are involved in this process, to a German collaborative process. Nico's involved in this, developing data acquisition systems and technique development to study particular applications of this measurement technique for specific applications of interest to that program, and a GCRF application, which is working towards understanding the complications of water processing, particularly from a South African perspective, undergoing 4 years of drought and understanding how pipes burst and water flows and blockages in pipes that don't have enough water is really, really critical. So we're working with the Advanced Water Institutes to understand better some of the problems that are inherent in this scenario. So we're using these nuclear techniques really to look at real problems in science. I think I've probably said most of this stuff already, but really to summarize, one of the things that I think is quite important from this, my expertise and interest really is in the instrumentation development. We're developing novel instrumentation, advanced computation, and big data processing. And this allows us then to apply these techniques to new and novel systems. And of course, those applications themselves will drive some of this development. So it is a cyclical process of research and development. And we've had a lot of success over the years in terms of the student body, but also in understanding physical processes for mining use, particularly in the South African context, but now looking to applying these techniques to other systems. And we're heavily involved in SENS, the South African Institute for Nuclear Technology and Science, in terms of education. I'm aware I'm getting towards the end of my time here, but here's a picture of just a few of our recent graduates who have come through the system, all of them presenting their work and a conference that we're all involved in. This is really nice to see the direct output from students that have been involved in this laboratory. And just from the context point of view, from COVID, there's where we were yesterday. And well, okay, well, we're all on Zoom. Isn't it fantastic that we're all on Zoom? But the lab is sort of open for business. We're looking, at the moment, we're still doing traditional PEPT in terms of minerals and mining applications, and the lab is running full speed ahead when we can around the COVID-19 restrictions. But we're now looking to build collaborations to apply this technique to other physical, chemical, engineering systems, particularly water sciences, but food, pharmaceuticals is a big one, energy sciences and carbon. So if you're interested in using this technique and developing that technique, or if you want me to talk to you in a little bit more detail about this, do contact me and we can talk about these things. So I'll put this final slide up then with a few links to our enterprise, to the website. And so that a lot of the physics that we're doing, some of this is fundamental physics. It's physics for discovery. It's understanding high energy physics. It's the CERN type things. These are the things that we're doing at the Department of Physics at UCT. But the other side of this is about development. It's about the human side of things, and using some of this applied physics to actually have some societal benefit. So with that, I think I'll stop and I'll happily take questions. Thank you for your attention.
Thank you, Tom. Any questions for Tom? We have one from Timin Lehin. If you would like to speak.
Yeah, thanks. I think I sent my question before you talked about the grad PhD projects coming out of the program. So thank you for the talk and great talk. So I guess my question was just basically like, are there plans to carve out a medical physics program at the University of Western Cape, since you guys are into stuff like that? And also, I don't think I caught any mention of postdoc involvement in this project. So I was thinking if you could shed more light on that.
Yeah, sure. So one of the things that we've always had ambition to is to pull some of this technology, the particle tracking, back into a medical physics type program. And part of the issue with that is finding somebody with a clinical interest. I mean, obviously I'm a physicist, I have no idea about medical type things. But there are some interests now, in particular on our detector development for things like small animal PET systems, and applying some of these techniques to medical physics type applications. So we are, and we have been in discussion recently with clinical workers from particularly Tygerberg Hospital, in terms of how we can adapt these approaches to medical physics. And we're also in collaboration with radiobiology at iThemba labs, where we'd be doing some sort of imaging of in vitro type samples for this. So there is an interest in that. I think one of the things, I mean, certainly graduate students, they go through either developing the system. I've a number of students that are working on the techniques themselves, but also a number of students that are applying the techniques to particular problems. So we do have students that are working through engineering who are using this technique to address their research questions. So that's an important part of this work. Obviously, there's no point developing the technique if nobody's using it. And you said about postdocs, I mean, I think that's a South African problem. I would love to have a postdoc, but actually there are all sorts of boundaries behind that. That's maybe something we talk about offline.
Okay, thank you so much.
Thank you. We have Georgie who has a hand up.
I have a question. Actually, you're showing that you're using some BGO crystals and photomultipliers for getting the position sensitivity. Did you consider any other technical solutions? Well, nowadays one can get on the market not that expensive silicon photomultipliers, which are certainly not sensitive to any magnetic field. So if one is thinking into that direction, and I suppose one can get them to very small sizes. So would that be an option, or did you think in that direction?
So yes, I mean, obviously these things are very interesting to us. From the BGO point of view, the advantage of this is it just gives us large scale, huge number of detectors covering a large volume. And on the micro scale, as I showed, we've been working with these cadmium zinc telluride segmented room temperature semiconductors, and they have very small pixels. Again, now we're looking at something this sort of scale, and we're looking at micro scale flows using those. We do, as part of some of the other nuclear applications at UCT, we're looking at silicon photomultipliers and digitization. But really, for these sort of applications, we need to do it on a scale that is really financially unfeasible. So they're interesting and they would be long term. I think, as I said, I've been awarded a grant to buy a PET CT system, and that would be only the 6th in the country. And that would be dedicated to this research. The next big grant would be a system that would actually do time of flight, because I think that would be a really interesting, just a high speed, high time resolution would be a really strong development for us. But on the other side of things, we are looking at these smaller pixels just for the higher spatial resolution.
Okay, thank you.
Thank you very much for the questions. Thank you, Tom, for your talk.
Thank you.
And now to continue our discussion